Okay, thanks, Lorenzo, for the introduction. Hi, everyone. My name is Yebo, research fellow at Singapore's NTU. For today's presentation, I'm going to present a very recent research project of our group, content-agnostic detection of cryptojacking with network traffic. I know most of you here are DeFi researchers. Well, this research was intended to study the cryptojacking problem from the perspective of network security. So I wish you are interested in this. Okay, so as we all know, cryptocurrency has appreciated rapidly during the last decade. Initially, when the concept of crypto mining was proposed, the crypto community was worried about whether the incentive or rewards are enough to motivate people to validate the transaction for the blockchain. But today, as cryptocurrencies become more and more expensive, we all know that the incentives or rewards are more than enough. So POW-based blockchains never worry about the lack of computing resource for validation. So crypto mining plays a very important role. In the blockchain system. It can validate transactions and add the valid transaction into the blockchain. It often divides mining tasks into among all the mining devices in a mining pool to get a better mining performance. It provides a mean for cryptocurrency to establish consensus, and such a mechanism also called proof of work consensus mechanism. Thus, miners can be treated as the infrastructure that supports the operation of most blockchains, most POW-based blockchains. Although crypto mining requires a significant amount of computing power to encourage crypto mining, most blockchains allow miners to make money via two types of rewards. One is the transaction fee, and another is the generation of new coins. For example, if a miner successfully commits a new block, it can get new coins as a reward. Thus, people can get a very considerable amount of profit by crypto mining. It is currently the easiest way to directly transfer your computing power to real money. So normal user-initiated crypto mining is that people use their own computing power to do dedicated mining to earn money or help the blockchain to maintain consensus. However, hackers can also steal other people's computing power to mine cryptocurrency and make money. This unauthorized behavior is called cryptojacking. There are many approaches can cryptojack other people's personal computer or servers to mine cryptocurrency for the hackers. For example, hackers can send a malicious email link that downloads crypto mining code when user clicks that link, and the code will be executed in the background of your computer or server. They may also create a website with crypto mining code embedded. Every time user visits a website, the browser will run the mining code to earn free money for the website owner. They may also simply compromise other people's server or PC, then install and run the ordinary mining software in the background. A recent emerging cryptojacking approach is through Docker images. So many people nowadays are using Docker's containers to deploy those software or web applications on their servers. Because it is a very easy and simple way for deployments. They only need to download the Docker images from the online libraries and deploy the image on their own machines. No need to worry about the system setup or dependency of software. However, many Docker images contain cryptojacking scripts and can automatically build crypto mining or cryptojacking software if deployed. Well, the Dockers are extremely popular among IT companies. Hackers can simply build such malicious Docker images with some very popular web applications and use people's server or personal computer to earn free money. For example, I can wrap up a GitLab web application with a Docker image and upload that online. And people, if you want to deploy the GitLab and you happen to like download my Docker image, you are cryptojacked. The most widely seen cryptojacking approach is still web-based cryptojacking. It is the most common approach. Sometimes hackers just compromise web servers and inject crypto mining malware. But for most cases, the website owners, they put the cryptojacking JavaScript code piece in their website's HTML header. So when the users visit the website along with the cryptojacking code will be downloaded to their computer and use their browser to earn free money. Like 2 years ago, when the cryptocurrency price was still high, for many small websites or even medium-sized websites, the profits they can earn from cryptojacking is actually more than the profits they can earn from advertisements. So sometimes if you go to some websites and you see your like CPU usage suddenly goes to more than 80% or even 100%, it's very likely you have been cryptojacked. And recently, cryptojacking has literally become one of the most major cyber threats people may face. We frequently hear the news that some public infrastructures are compromised to mine cryptocurrencies for hackers, such as a workstation in airports and servers in data centers, because those machines are for specific purpose. Once they are functioning, the maintenance people don't really care whether they are compromised or not. Here I show you 2 recent reports. One is about GitHub. GitHub is investing a crypto mining campaign that abuses its server infrastructure. So GitHub server infrastructure is everywhere. People may use it to build a website, to build a web page, or like to do some like see in and see out like pipelines. But it can be abused by hackers to mine cryptocurrency. And another is that people find that cryptojacking malware are widely installed on unpatched Microsoft Exchange servers. So cryptojacking not only consumes a large amount of power, but will also occupy the computing resource of other people's computer or servers. The computing resource of an individual can be treated as someone's personal property. Besides, it can potentially bring some damages to people's hardware, as they are very heavy loaded computing tasks. So to solve the cryptojacking problem in both academia and industry, many approaches have been proposed. Most of them are endpoint-based solutions. Endpoint-based solutions, you have to, for endpoint-based solutions, you have to install some softwares on the endpoint. For example, malware detection approaches that can detect the cryptojacking program patterns running on your computer. Or like some endpoint-based anomaly detection solutions, they don't analyze the software's memory, they analyze your computer hardware usage. If your CPU usage is very close to the heavy load hash rate, hash computation, then it will probably rise an alarm saying that you are doing crypto mining. If you are using some updated antivirus software like CloudStreak or McAfee, you should probably see such designs in their software. However, for almost all the endpoint-based solutions, it is impossible to ensure that they have been deployed on every single machine. Most people just don't have those security software on their computer. Actually, most of the computers on Earth are unprotected, and also they are not compatible to some IoT devices. There are also many in-network-based solutions that have been used in the industry. For example, this block list-based solution, mostly proposed by Cisco. They just block all the traffic related to a mining pool IPs, thereby stopping crypto mining. However, mining pool IPs can be very dynamic. It is almost impossible to maintain an accurate and up-to-date IP list. There are also DPI-based solutions. So DPI refers to deep packet inspection. they do deep packet inspection on each single IP, on each single IP's packets, and match if there are any crypto mining keywords. However, such an approach may raise some privacy concerns, and they also need to analyze the content of the user packets. They also don't have the ability to handle encrypted network traffic. And recently, we have seen many approaches apply traffic analysis to solve the cryptojacking problem. So some background knowledge about network traffic analysis. It is a technique that infers the application layer knowledge only by analyzing the transport layer or network layer information. So even when the network messages are encrypted, for example, you can analyze the size and the frequency of your network packets to infer like whether you are simply visiting a web page or you are doing some video streamings. Such an approach does not rely on deep packet inspection, and they only detect cryptojacking traffic by matching the traffic patterns through like S-flow or net flow, which are purely like metadata of the network. The advantage of such approach is that they are very easy to deploy. For example, for a network operator of UCL, you only need to tap the traffic from UCL's main router, and then you can protect all the devices within the UCL campus. However, they are not very accurate to operate, and they cannot do some like fine-grained differentiation. For example, they are almost like impossible to distinguish cryptojacking traffic from normal crypto mining traffic or user-initiated crypto mining traffic. So our proposed research intends to study and measure the traffic of normal crypto mining and cryptojacking traffic. And then we want to use the measurement result to design cryptojacking detection approach purely based on traffic analysis. It not only detects crypto mining devices, but it also distinguishes cryptojacking traffic from user-initiated crypto mining traffic. It's a very fine-grained application layer knowledge, and it should be efficient enough to conduct real-time detection for like a campus level or company level network. And we want to evaluate this approach with real-world network traffic data. So before diving deep into our findings, so let me first give a very brief introduction to crypto mining, in case some of you don't know it. Here is a very high-level structure of a blockchain. So each block is connected with its neighbors by the block header. Also, the block header connects the block's unique transaction sessions. At one moment, there could be many unconfirmed transactions in the network. The miners need to collect a certain number of transactions, validate them, form a Merkle tree, and calculate the correct block header, and add those transactions to the blockchain. This process requires a significant amount of computing power, but as a return, the miner can get the transaction fee and a generation of a new coin as a reward. So here is an example from block header. Of the block header, it comes from Bitcoin. So the first attribute is the hash value of the previous block's header. In Bitcoin, it's doing SHA-256 twice on the previous block header. So it's kind of like a chain. Every block is connected to the previous block. Then it has a hash value of Merkle tree root. All the transactions are stored as Merkle tree nodes. Any tiny change on the transaction will result in changes in the Merkle tree root. So once the Merkle tree root is determined, transactions are immutable. In the end, most importantly, we have a nonce, which is an arbitrary number determined by the miners. So mining is essentially changing the nonce, changing this number, so that the result of doing SHA-256 twice on the block header can like satisfy certain criteria. For example, the first n bits are 0 in this case. As hash functions are one-way functions, you cannot derive the input based on the output. So the only algorithm to achieve the goal is to enumerate all the possibilities and find out the correct answer. The more calculation the miner does, more likely it will get the correct result. So this mechanism is called POW. And a very important concept here is the hash rate, the speed at which a device can complete a hash operation in crypto mining. So higher hash rate a device has, more quickly it can complete a mining task. And nowadays, as difficulty for mining is extremely high, it could take decades for a personal computer to confirm a new block. So to get stable income, miners must form a mining pool to increase the overall hash rate. A mining pool is a pooling of resources by miners who share their processing power over a network. And in the end, they split the reward according to the amount of work they have contributed to finding a block. So the communication between the miner and the mining pool should follow certain protocol so that miners all around the world can join and quit the mining pool seamlessly. Streedom is a protocol that almost all the miners are using. You can follow Streedom protocol to join any mining pool on Earth to mine cryptocurrency for the pool. Here is a figure that can illustrate the mechanism of Streedom protocol. We have collected the mining packets and conducted deep packet inspection and made this figure. By using mining pool, the mining procedure changes from peer-to-peer communication to server and client mode. The miner first needs to register itself to the mining pool, and then the mining pool will return with the login confirmation. And followed by that, it will send a sequence of assignment allocation messages to the miner. And once the miner completes any one of the assignments allocated by the mining pool, it will return a result message to the mining pool. And here is the visualization of the mining traffic with Monero mining, XMR crypto mining. The upper subfigure represents the outbound traffic, which means it's the traffic sending from the miner to the mining pool. The subfigure beneath shows the traffic sending from the mining pool to the miner. And the x-axis represents the time measured by seconds. And the y-axis shows the size of packets measured by bytes. So as we can see from the figure, like the outbound traffic is dominated by the result submission messages. There are also a bunch of other messages. Those are purely like TCP protocol control messages, like TCP ACK, TCP SYN, TCP FIN messages, just to make sure the connection is always open, and to make sure like the mining pool can acknowledge that they received our like messages. And the inbound traffic is dominated by the assigned allocation messages in a much higher frequency for several reasons. First of all the mining tasks can expire quickly. The mining pool needs to make sure all the clients, all the miners have the most up-to-date assignments to work on. Also, like the mining pool always needs to make sure all the miners are always in the busy status so that they can work hard on the mining task. So the frequency of assigned allocation message is significantly larger than that of result submission messages. The packet size of crypto mining traffic is also very different compared with other types of traffic such as video streaming, Skype, HTTP website traffic, Steam, Zoom, or DMS. The size of crypto mining packets are more concentrated in a very small range, always range from 55 bytes to 450 bytes. But for most of other packets, they can be as large as like 1,500 bytes in size. They cannot be larger because like the size is limited by the MTU, maximum transition unit. If you have a packet larger than this size, it will somehow be cut by some routers along the path, split into two packets. And of course, we also find some other traffic has similar packet size distributions, for example, NTP packets. And we also measure the packet frequency, and we found that the frequency of assigned allocation messages is very stable, but the frequency of result submission messages, they are unstable based on the hash rate. The higher hash rate a device has, higher frequency it has for like result submission messages. The packet interval is like the fingerprint of an application. Like the interval distribution for crypto mining traffic is also very unique. On the left-hand side, it shows the packet interval distribution for inbound packets, which means it's the packets sending from the mining pool to the miner. On the right-hand side, it shows the outbound packets, refers to the packets sending from the miner to the mining pool. We can see the inbound and outbound packet distribution are very unique. The majority of the assigned allocation messages will appear after a certain time. Like this is due to the assigned allocation algorithm used by mining pools, while the outbound packets interval distribution is different in terms of the, this feature. And our detection approach will utilize this knowledge for traffic identification. Still, the goal of our approach is not only to detect crypto mining traffic, but we want to do some further analysis to distinguish between cryptojacking and the user-initiated crypto mining. Thus, we further studied the differences between cryptojacking and the user-initiated crypto mining. So we found that cryptojacking sometimes are more sneaky than user-initiated crypto mining traffic, because hackers, they want to monitor the status of the miners and adjust the hash rate according to the current machine status to avoid being discovered. So usually in almost every like open source cryptojacking software, they have such features to adjust the speed you want to use to mine cryptocurrency, and they can be automatically adjusted based on the condition of the current machine. And also, for most cryptojacking, the hash rate are essentially unstable. The first reason is that usually hackers are very difficult to get the admin authority of a machine, so that they don't have the authority to use the full power of a device to mine cryptocurrency. And also, the cryptojacked devices are very diverse. They may be IoT devices like your smart TV. They also may be some like personal computers. Some may be servers. So it turns out like we have measured the hash rate differences between the cryptojacking and the user-initiated crypto mining. The blue line shows the user-initiated crypto mining as a hash rate, and the red line shows the cryptojacking's hash rate. We can see that the user-initiated crypto mining traffic, the hash rate is almost higher than cryptojacking in every case with the same hardware, and they are like more stable compared with cryptojacking. So we will further utilize this knowledge for our further detection. So here is our proposed approach. Our method is called CJ-Sniffer. So it's the operation model of our approach. Our approach is designed to be deployed on the router or a switch of a computer network. This network could be a small size live network, could be some medium size like company or campus network, or even like small size internet operator. For example, the East London network operator, things like that. And it needs to get the content-agnostic traffic, and we use S-Flow to capture this information. So S-Flow works as for every single packet passed by the router, it will simply sample the header of the packet and forward this header to our system. So the header information is considered as public information on the internet. All the router needs to know the header information to reroute the traffic. And it would totally drop the content information, which means it's the payload information will never be analyzed by our approach. And behind the router, they could be many different devices, could be like personal computer, IoT devices, or like data center. Like once our approach is deployed on the router, we propose that it should be able to monitor and protect all the devices behind the router. So the first step is pre-processing. So our approach is a traffic analysis-based approach. So CJ-Sniffer fetches the information from the baud router or switch, and CJ-Sniffer will first filter out irrelevant packets, such as packets of different protocols, packets from the whitelist, and then it will group the packets and group the packets by connections and store all the relevant information from the same connection in a gigantic hash table. Because we want to achieve a real-time line speed for the analysis, we have to use some in-memory based storage technique and use some hash table to quickly do some queries on the stored information. And yes, as I mentioned before, CJ-Sniffer is a content-agnostic approach, which only captures 4 types of information from the inbound and outbound traffic for the detection, which are source and destination IP address, source and destination port number, protocol type, and packet size. And those information can all be provided by almost all the traffic capture engines like NetFlow, SFlow, or JFlow. And based on the pre-processed information, CJ-Sniffer conducts a cryptojacking traffic detection in 3 phases. The phase 1 is to filter out obviously irrelevant traffic with packet size. So in a network, almost 99% of the traffic are totally unrelated to crypto mining, not even alike. So this step can significantly reduce the data volume by more than 98%. And we just use some simple rules of packet size to do this type of filtering. And after phase 1, we get a bunch of traffic could be suspicious to crypto mining. So for the detection of crypto mining, we do that by matching the packet interval distribution. As I mentioned before, the packet interval distribution of crypto mining traffic is very unique. Thus, CJ-Sniffer utilizes KS test to match the distribution. So KS test is a very efficient approach to test whether 2 data samples are coming from the same distribution. Compared with other distributions such as t-test, it has no requirements on the number of samples. The idea of KS test is simple. We just build 2 cumulative distributed functions for both training data set and the traffic data for inference. And then we scan from the very left to the very right and capture the maximum differences between the 2 functions and try to figure out whether this difference is larger or smaller than a threshold value. The problem of this approach is that the time complexity is high. In average, it takes O(n) log n to build the CPF function for data samples. Therefore, to accelerate the detection process and make it able to deal with a large amount of traffic, maybe 100 gigabytes per second or even 500 gigabytes per second, we made some optimizations on the detection procedure. We pre-developed the coordinate system of the CPF into K parts, and this allows us to calculate a approximate CPF function faster than the CPF function of the training data is pre-built. And in the end, the time complexity of the KS test is increased to O(n). And after phase 2, we already have network traffic classified as crypto mining and non-crypto mining. as our goal is to further differentiate the cryptojacking from the user-initiated crypto mining, we just dropped all the non-crypto mining traffic at this phase and further use an LSTM model to capture the tiny differences in the hash rate. According to our measurement result, the hash rate of user-initiated crypto mining will be more stable, resulting in more stable outbound traffic. And this difference can be perfectly captured by the LSTM model. So to conduct this research, we, for both traffic measurement and approach testing, we collected around like 800 hours of crypto mining traffic in PCAP format. So it can be easily converted into SFlow or NetFlow and become content agnostic. The crypto mining traffic we collected contains both normal crypto mining traffic and CryptoJacking traffic from Monero, already labeled. And we use different computing devices to collect the crypto mining traffic, including CPU, GPU, and even IoT devices. So our research is mainly based on the CryptoJacking of Monero. Because Monero is the dominated cryptocurrency for CryptoJacking. I would say almost the only choice for many hackers. There are several reasons for that. First of all, Monero is totally a privacy-preserving blockchain. People cannot trace back to individuals according to the transactions. And also, Monero's hash function is very special. It uses CryptoNight as its hash function. People can get countable profit on almost all the devices, including CPU-based platforms, GPU platforms, or even IoT devices. Because when people design the Monero, they want to encourage all the individuals into the mining or validation process, rather than like enabling like several like large parties to do all the mining and the validation. So for other cryptocurrencies like Bitcoin, you get nearly zero income when mining with personal computers. So, which makes like Monero almost the only choices for hackers to do cryptojacking. So we first evaluated the accuracy of crypto mining detection. Here are some heat maps showing the evaluation results. The x-axis shows the time it takes to generate the result, measured by minutes. And the y-axis shows the hash rate. And the thing is, as we are using a statistical approach for crypto mining detection, the more data sample we get, more accurate result it can generate. In order to get more data samples, there are two ways. One is to like increase the time for data capture. For example, if you only capture the data for 5 minutes, for some like low computation power devices, they almost generate like 2 or 3 packets for result submission. That's almost unusable. So we get like a very not so good accuracy when the time is very short. But if we increase the data capture time like to half an hour, the accuracy becomes very decent. And another way to increase the volume of data to be collected is like if the device has a higher hash rate. The more hash rate a device has, more result submission messages it can generate within a short time period. So the accuracy of our approach can vary, like depending on which circumstances you are facing. And typically, if the data capture time is like more than half an hour, we can get a usable and decent accuracy rate and false positive rate and false negative rate. Then we also evaluated the efficacy of cryptojacking traffic with efficacy of cryptojacking traffic detection with different system loads of background process. The story is, if the background process of a system is higher, more unstable the cryptojacking hash rate is, and the easier the LSTM model can capture the differences between cryptojacking and user-initiated crypto mining. So if the system load of the background process can be higher than 40%, we can detect like more than 90% of the cryptojacking traffic. if it is higher than this value, we can detect almost like 98% of them. However, if the background process, the system load is lower than a threshold, our approach may be a little bit more difficult to detect them. And of course, we want our approach to catch up with the line speed, which means we need to like minimize the processing delay to analyze the traffic. So we also evaluated the processing delay of CJ-Sniffer under different operation circumstances. When facing the network with different thresholds or different packets per second, it has different processing delays, but always like no matter how large if the traffic throughput is as large as 10 gigabits per second, we can still like generate the result in average like within like 0.1 seconds. It's like, we can say it's line speed. Some limitations and open issues of our approach. Traffic analysis is also still easy to be deceived. People can choose to add some dummy packets. They don't carry any content. They just add those packets to escape traffic analysis, or they can delay certain packets. However, we did not see such designs on current like open source cryptojacking software. Also, it may be difficult for them to delay certain packets because once you get a result, you need to submit it as soon as possible. Otherwise, the result can be expired or calculated by other miners. Still, it might take a relatively long data collection time to get a very decent accuracy. But I think the time is still feasible because once you can monitor a device for more than like half an hour, we can get a very decent accuracy. And the coverage of the collected dataset can also be further enhanced to detect more types of crypto mining traffic. Now, let me talk about some initial ideas about future research. It is a very still an ongoing project, slowly moving on. So with CJ-Sniffer, we can already identify crypto mining devices in the network and further classify them as user-initiated crypto mining devices and cryptojacking devices. However, there are still many other types of devices existing in the network. For example, ordinary clients, HTTP servers, validation nodes for different blockchains such as XRPL nodes, Federa nodes. So can we do a comprehensive fine-grained classification approach on those devices and identify all of them only by analyzing their traffic? This is very useful because people claim that blockchain is a totally decentralized approach to like store data or to validate transactions. No entities can simply ban all the blockchains in the world, can ban all the nodes in the world, but it turns out to not be so true from the perspective of network traffic analysis. If we can identify all the, for example, Bitcoin validation nodes in the network operator itself can simply do some access control on those nodes and simply remove blockchain from the earth. And also, this approach is also very helpful to like malicious activity detection, because traffic analysis is a perfect approach to detect intrusions or anomalies for devices. But the problem is the devices under the router are very diverse. They are servers, they are clients, and they need to be used. The strategy for intrusion detection for those devices are totally different. If we can identify the identity of the device behind the router, it will make the intrusion detection much easier for the network operators. So what we do is to build a profile for each devices in the network by purely analyzing their network behavior, their traffic patterns. And then we analyze those profiles and classify those devices And we further detect anomalies by analyzing each endpoint's ongoing behaviors because their profile will change. We can compare their profile today with the profile yesterday to see whether it is infected or not. So here is a profile we are currently doing. Like it's a two-dimensional matrix. A profile is a snapshot of endpoint's daily behavior. So the two-dimensional matrix contains the timing information on the x-axis and the port information on the y-axis. And each cell stores the specific attributes or features for this slot. For example, 12 o'clock on port maybe 443, how many traffic you have sent. And as this matrix is a sparse matrix, we don't need to waste space to store zero numbers. We use a nested dictionary to store such profile. It only takes like several kilobytes for a machine to store 1 day's profile information. And if the network operator has millions of devices in the behind its network, it only needs several gigabytes to store the profiles for all the devices, and they can do this all the days. It's kind of like a log, but it can easily log all the devices' daily behavior for a very long period. For example, here is a visualization of a client's profile on August 17th. So this bar represents the outbound traffic, and this bar represents the inbound traffic. This y-axis represents the service port, and this y-axis represents the non-service port. And on the x-axis is the timing information. From this profile, we can tell a bunch of informations. For example, we can tell the active time frame for this specific client is from maybe like 8:30 a.m. to like midnight, because it receives a bunch of traffic, mainly from its non-service port. And we can also see what type of web application this client is visiting. For example, it sends a large amount of traffic to port 443, which means it's purely using like HTTPS service from like approximately 9 a.m. to midnight. And we can do this for all the devices. For example, we can do this for the servers. And the different types of server will show different characteristics on their profiles. We can easily classify their identity based on those profiles. The approach currently we are testing is through a very easy hierarchical clustering approach. For example, if we just generate a simplified profile from the original profile, we can get the port usage information of its device. And then we do a hierarchical analysis. So in the hierarchical analysis, the x-axis represents the features. The y-axis represents different entities. In a hierarchical clustering, we use agglomerative approach. It will build a classification or clustering tree on the left-hand side. And we can determine the clustering granularity in a very explainable way. For example, if we cut a line here, we probably like divide all the devices into 4 categories, like server, non-server client, IoT devices. Of course, it's only an example. And currently, we are still testing. For example, we sampled like 200 IPs profiles and built such hierarchical clustering tree. And we successfully get a server group and a client group. And then we want to inject some traffic from the blockchain validation node to see where those traffic is in the tree. And we will classify all other nodes near the tree's leaf as blockchain validation nodes. And we can even do some finer granularity classification to do this for different types of blockchain validation nodes. And that's our plan, but it's still an ongoing project. So let's go back to CJ-Sniffer. So CJ-Sniffer, conclusion, CJ-Sniffer is a privacy-preserving cryptojacking traffic detection approach, only relies on content-agnostic network traffic data. And not only it can detect crypto mining traffic, it can further distinguish between user-initiated crypto mining and cryptojacking. And it features high efficiency and easy deployability. That's pretty much everything for my presentation. Let me know if you have any questions.
Thank you very much, Dr. Feng. Let's open the floor for questions, observations, comments. Anyone?
Yeah, go ahead.
Well, I can start with one. So when you are measuring the prediction accuracy, so the true value of cryptojacking, how did you do it? Because I see that you need to go to the actually the code to see if there is a line of cryptojacking code embedded in there. Is that process done manually to find out what is the true value or the ground truth?
The ground truth is generated by us. So we downloaded a bunch of cryptojacking software, running them on some machines with different setup and status, and capture their traffic. And we already know the ground truth of the traffic because we generate those traffic.
I see. So it's kind of simulated. You generate yourself with the
Yeah.
So I remember one of those slides where you put
Yeah.
Okay, understood. The second question about Monero, I could probably just look up online, but if you understand this a bit more, you're saying that Monero using a hash function that would allow small devices to also profit. So we understand, like for Bitcoin, because of the proof of work consensus mechanism, the probability of getting the reward is proportionate to the computing power that you control, right?
Mm-hmm.
So what is it with Monero that allows even like small devices to be able to get rewarded? Is there some kind of is it proportionate to number of devices? Apparently it's not proportionate to computing power then.
They are all determined by the computing power, but the difference is for Bitcoin and the previous Ethereum 1.0, their hash function can be optimized by special like hardware designs. You can easily use like GPU-based architectures or ASIC chips to optimize the hash rate, to optimize the performance. But CryptoNight is different. It's very difficult to be optimized by some hardware architectures.
Okay.
But they still like determined by computing power.
Okay.
Yeah.
Thanks.
Thank you.
Yeah.
Okay. Thank you very much for the talk. My question is mainly on how practical the solution is. Have you measured the cost of your approach? Like what's the CPU usage, etc. And
Sure. We purely did all the experiments on personal computers. It's totally feasible because network traffic analysis is already widely used for a couple of decades, and it's used in very large scale. Like, for example, I don't know whether you are aware of that. Almost all the companies, all the network service providers, they will do some traffic analysis on their routers to determine whether there are some DDoS traffic or some other intrusions exist. You can even do that for entire country. For example, China's Great Firewall. The performance is not a bottleneck. The bottleneck is mainly on the false positive rate and the accuracy you can achieve, because the false positive rates really matters in traffic analysis. You are receiving traffic from millions of devices. Even your false positive rate is 1%. They will still be thousands of devices get unconnected to the internet simultaneously. So our main focus is more of minimizing the false positive rate, but still maintain a usable true positive rate, rather than trying to like making it like less dependent on the computing resource. From the computing resource perspective, it's totally feasible.
So just a follow-up question. This paper is mainly like content-agnostic approach, right, into the detection. So do you see any benefit in actually checking the content sometimes, like maybe a hybrid approach, to reduce the detection time and maybe lower the false positive rate?
Yes. If you can check the content for like, because like almost like 80% of the crypto mining activities, they are unencrypted. You can totally identify all of them with nearly 100% accuracy by only checking the content. But there are still a small portion of crypto mining traffic, they are encrypted, like using some SSL, like SSH protocols. However, like there are some regulations, like in United States, or I guess also in European countries, network operators have limited like power to check users' content, like because people just don't want all their network contents to be monitored by their network service providers. Yeah. You get some benefits, but you get more trouble, I would say.
And I have a final question, if you don't mind. So in the data collection process, would you mind elaborate a little bit more on what kind of machine you use to like collect data from different devices? And
yeah.
What's the apart from the mining software that's running, right? Is there anything else you're running on the machine in order to like basically how do you produce that false positive samples?
So we have collected the mining traffic from different types of machines with different chips, both like GPU-based architectures and CPU-based architectures, servers and personal computers, and also even for IoT devices, we use Raspberry Pi 4 to do all the data collection work. And we collect our data from two gateways. One is our lab networks router, another is our campus networks router. And we run those machines in different circumstances. For each machine, we try to adjust their like background process overhead from 0% to 100%, and run both like CryptoJacking software and crypto mining software, and to collect their data. Yeah, that's our approach.
Right. Okay, thank you.
We do have time, yeah.
Yeah, thank you for the talk, very nice. So I'm wondering like how easy it is to bypass or escape your detection by, for instance, as I said, like add some dummy packets into traffic.
Yeah. It depends on how many dummy packets you are adding. If the thing is, you also need to achieve a balance, because dummy packets would decrease your network throughput. For example, if you want to like fully escape our detection system, you probably need to like, for every packets you send out, you need to add some dummy packets to cheat the system. Then your network throughput would decrease by half. So it's not like easy that you want to escape our system without sacrificing anything. You need to sacrifice your network bandwidth, your network delay to do this. And also, if you simply add several dummy packets, you are not sufficient to generate enough like statistical features to bypass the system. So it depends on like how much you want to sacrifice. But if you do that, it's totally possible. You can escape.
Any last question that we want to ask? This is the time to speak. No, I'm checking. So I do have maybe one final question here. Do we have a sense if crypto mining or cryptojacking really is stable compared to what it used to be before? If it's essentially also a function of how the markets are going, or it's a problem that, it's kind of independent out of that, the amount, let's say the total amount that people do these kind of activities?
Oh yeah, it's affected deeply by the market situation. For each like POW based blockchain, you can check their like whole computing resource witnessed like online. They have a chart to record all of them. Like you can see when the price of cryptocurrency is high, the computing power like witnessed by the whole network will be increased significantly. So I would say there are some connections between those two factors. However, from the perspective of like mining traffic detection, it may not be affected by those market changes. Like from the perspective of individual device, the behavior of them tends to be stay as usual. Yeah.
Okay, thank you very much. And if we don't have any further question, please join me in a round of applause.
Thank you.